In the previous lecture, we were discussing population growth models or exponential growth models. Uh, growth and decay models. In the population growth models, we discussed that any population which grows at a certain rate that can be modeled by using the equation dp by dt. It is proportional to basically p, where p you can say that p of t, where t is time. Sorry, population at a certain time. Okay, uh, population of some uh, of some certain biological organism, you can say, or a human population at any time t. If we write it properly without this sign of proportionality, then we can write this is some kp, where k is what? Growth rate. Similarly, in population decay models, the population is always basically proportional to its current population. But in this case, we have a negative sign here, negative lambda at p, where negative lambda is the decay rate or the decreasing rate of the population. Let me admit the people. I hope you get it. Let's हमने एक example भी देखी थी इसकी. If we have, let me have another example. Population, this one. A culture of bacteria, this example is given in my notes. You can see it from there. I just read it here. Example. A culture of bacteria grows proportion to its current population if the bacteria grows at a rate of 10% per hour. What is the growth rate? Growth rate, you can say it is K, and it is 10% per hour. 10% per hour. What will be the population of bacteria in one day? So we need to calculate, let P of t be a population at any time, then we need to calculate population after 1 day. P of t after 1 day. So 1 day means if we convert it in hours, because the growth rate is given in R, then we have to calculate the population after 24 hours. So what would be the differential equation corresponding to this this requirement according to these conditions? The growth rate is 10% per hour, and we have to compute population after 24 hours. So this phenomena or this physical process will be modeled by dp by dt 0.01 times p, because 10% is the growth rate, and initial condition is what? There is no initial condition, so it means p at 0. P at 0 is, and it is given that the population, initial population is 500. So P at 0 is 500. So this is what we have, the mathematical model corresponding to the given example. The population of certain bacteria, it grows at a rate of 10% per hour, and we have to compute the population after 1 day, means 24 hours. So this is a very simple model which only gives us the population between a certain time where we assume that no bacteria dies. Okay? There's only growth in population. There is no decay in the population. In addition, अगर हम इसी example में ये भी कह दें, if we say that the bacteria die at 5% rate each hour. Okay? If we add in this question that the bacteria dies at a rate of 5%, then the decay rate or decreasing rate is, decreasing rate, you can say it K, maybe lambda, and the decay rate is 5%, means negative 0.05. Okay? So the bacteria die at a rate of 5% per hour. Then in this equation, what we have to include, we have to include the decay rate, which is negative 0.05 of the population at any time. So this will give us another model which tells us that, which includes both birth and death rates. So this is basically, you can say, a more advanced version of the model which we have discussed in the previous lecture. If in another situation, if we say that 500 or maybe 200 or 100 bacteria, 100 bacteria migrate from some other place, okay, and include in this place where we are assuming that there are initially 500 bacteria. So what we have to include in this case in the model, okay, what we have additional condition here, we are assuming that 100 bacteria per hour, okay, in each hour, 100 bacteria, they come into our place where we have initially kept the 500 bacteria. Okay. What we have to include in this model, then we have to include here plus 100 bacteria. Okay. So this will be our mathematical model in this situation. Okay. So initially क्या था, 500 bacteria से, उनका growth rate क्या था, 10% in each hour. उनका death rate क्या है या decay rate क्या है, 5% in each hour. And we are assuming now that the 100 bacteria are migrating from some other place to this place, or from some other container to this container, okay, in every hour. Then our mathematical model will become this one. So जितनी assumptions या जितनी situations हम इसमें add करते जाएंगे, mathematical model हमारा जो है वो क्या होता जाएगा, improve होता जाएगा. ठीक है. Another condition, अगर हम कहते हैं कि 10 bacteria जो हैं वो in each hour हम उस कंटेनर में से निकाल लेते हैं, ठीक है, 10 bacteria. So what we have to do, -10 in every hour. So our mathematical model will be this one. It will be basically increasing or improving by including every assumption in this model. I hope you get it. If you have any question, you can ask me. Now we can simplify this thing and get the model. आप इसको simplify कर सकते हैं. 0.01 minus 0.05 p plus 100 minus 10. ठीक है. So what is this? This is your growth rate. This is your decay rate. And this is basically some migration factor, ठीक है, 100 bacteria. And this is what you are taking out of that container. I hope you get it. If you have any question, you can ask me. Hello? So if you have any question, you can ask me. This is the mathematical model along with this initial condition now. Okay. If you have any questions, you can ask me. I hope you can solve it. This mathematical model now turns into or becomes dp by dt is equal to 0.05 p plus 90 along with the condition, initial condition p at 0 is equal to 500. Some noise here. Yes, the growth rate is 0.1, not 0.01, because it's 10%, so it is 0.1 here. Huh. Okay. So thank you very much. So this will be your mathematical model corresponding to this situation. I hope you can solve it and you can find the population after 24 hours. You have to solve it. You'll get the solution in terms of exponential function, and then you can calculate the constant of integration by using this initial condition, and you can later on you have to just put p of t, p of 24, and you will get the population after 24 hours. Now there is another situation in which we are not directly given the rate of growth or the growth rate. Let's do another example of this situation, and then we shall discuss the radioactive decay or the radioactivity. Another example. If you have any question in this example, you can ask. Kindly mute your mics. किसी का मोबाइल बोल रहा है. So another thing is for example, the rabbits, the certain population of a rabbit increases at a rate of what? 15% in 8 hours. या यहाँ पे bacteria लिखा हुआ है, आप ये लिख लें. So, a culture of bacteria grows proportion to its current population if the initial population of 500 bacteria. Now, in this example, it's a culture of bacteria. Okay. Initial population, P at 0 is, again, you can say 500. Last example जो हमने की थी उसी को हम थोड़ा सा उसकी situation को change कर रहे हैं, ठीक है? If the initial population of the bacteria is 500, which increases by 15% in 8 hours. Now the growth rate is which you can say K, is 15% in 8 hours. And what will be the population in 1 day? Now we have to calculate population in 1 day means P of 24. We need to calculate it. 24 hours. Now the growth rate is in every 8 hours. It's not per hour. So what is missing here? We cannot say that K is equal to 0.15. This growth rate is basically given in every 8 hours. You can say that in every 8 hours. Now this should be given per hour, means in each hour, means in every hour. Now, the growth rate is not clearly given here. What we have to do, first we have to calculate the growth rate per hour. How can we calculate it? We know that the initial population is 500. Okay. P of 0 is 500 and P of 8. Population after 8 hours will be what? 500 plus 0.15 into 500. Okay. Initial population is 500 and population after 8 hours will be, after first 8 hours, you can say that 500 plus 15% of the 500. Okay. So if we solve it, you can say this 501 plus 0.15, which is 500 multiplied by 1.15. Okay. If we simplify this, we get 575. Now, after first 8 hours, the population will be 575. Now, using this, we can compute the K. As we know that if we solve the growth rate equation, basically dP by dt is equal to K times P. We need to compute K at every hour, the growth rate per hour. If we solve this equation, what do we get? P of T is equal to some constant C naught exponential of KT, where C naught is what? It is initial population, it is 500. Yes? Any question?
Can you please adjust the camera?
Okay, sorry.
The camera is on the other one.
Sorry. Now, the population growth model, there is only the growth phenomena in this model involves. So what we have to do, we have to solve this equation. What do we get? We get this kind of solution where C naught is constant of integration. If we solve that constant of integration using initial condition, C naught must be 500. So now P of T is what? It is 500 times e raised power kt, where k is unknown. We need to calculate, we need to compute K first. Now, after 8 hours, we know the population. It is what? It is 575. After 8 hours, if we insert it here, P at 8, then it is 500 times e raised power K times 8, because time is 8 hours. Here, K is unknown. P at 8 is what? We know it, 575 is equal to 500 times e raised power 8k. Now, in this equation, only k is unknown. We can compute k from here. So now we divide this thing on the other side. What do we get here? It is 0.1747, 0.01. So you get K after solving this equation by taking log on both sides. I hope you can solve it. K is approximately equal to, you can say, approximately equal to 0.01747. So this is your growth rate per hour. Now this is your growth rate per hour. Now you can calculate by using the similar differential equation. Now you can solve this differential equation. dP by dt is equal to, where K is what? 0.01747 times P. So its solution must be P at T is equal to 500 exponential of 0.01747 times T. Now you can compute the population after 24 hours by inserting T is equal to 24, and we have 500 times 0.01747 times 24. Now after solving it, you should get the population after 24 hours. And it is 760, approximately 760 bacteria. Approximately, because जो decimal में values होंगी, you have to ignore them because the number of bacteria cannot be in decimals. I hope you get it. If you have any question, you can ask me. So the growth rate must be given per hour, per day, or something like that. So if the growth rate is given unusual, we have to compute first the growth rate per hour, or maybe per day, or maybe per year. Okay. If you have any question, you can ask me. Now, the next thing which we are going to discuss is the radioactive decay. Decay models, maybe you can say, or you can say radioactivity. Now, what is this radioactivity? There are many materials, for example, uranium, polonium, and there are certain other kinds of polonium as well. These kind of materials, their nuclei, they emit certain elementary particles from their nuclei, and they reduce in amount in certain time. ठीक है, बहुत सारे जैसे आपके पास यूरेनियम है या पोलोनियम है, they decay with time because they emit certain elementary particles out of them. So their amount is decreasing with the passage of time. So this kind of phenomena is called radioactivity, and we, in mathematics here, we call them radioactive decay models. How can we model the age of certain material? For example, uranium है, so उसकी कितनी एज होगी, मतलब कितने टाइम के बाद उसमें से कोई भी एलिमेंट्री पार्टिकल्स जो हैं एमिट नहीं होंगे या रेडिएशंस एमिट नहीं होंगी, क्योंकि आपको पता है इस तरह के मटेरियल से रेडिएशंस एमिट होती हैं. एक्चुअली इनफैक्ट क्या हो रहा होता है, बेसिकली उनके जो न्यूक्लियसेस हैं उनमें से एलिमेंट्री पार्टिकल्स, इलेक्ट्रॉन, प्रोटॉन वगैरह, आई थिंक they are leaving that nucleus. So these kind of materials, they decay with time. So these kind of materials, we model them dN by dt is proportional to basically, or you can say negative mu of n, where negative mu is what? It is rate of decay. Okay. So where n is what? It is the amount of that material substance of. This is amount of any substance, any radioactive substance, you can say that. Radioactive substance. So these kind of models basically have been discussed by Frederick Soddy. Frederick Soddy in the start of 20th century. So we are going to model radioactive decay of certain materials by using these kind of models, where you can say that n of 0 is what? N of 0 is the initial amount of that substance, radioactive substance. For example, let us discuss this example, this one, a polonium 218 example. Polonium 218. 218 is a certain radioactive substance which decays over time. Okay. This material decays exponentially. The decay rate is means decay rate is negative 23. Decay rate है तो फिर definitely negative होगा, ठीक है, negative 23.1%, ठीक है. It's the decay rate per minute. And we have to find the equation that satisfies this situation. Okay. Find the ODE. Second, what we have to, if 100 grams of polonium 218 is present at t is equal to 0, the second question is, if 100 grams of polonium 218 is present at t is equal to 0, at t is equal to 0, then what will be the amount of polonium after 90 seconds? What is amount of polonium 218 after 90 seconds? 90 seconds means, okay, we are given the rate per minute, and we have to calculate the amount of polonium after 90 seconds. Either you convert that rate into seconds, or you convert this thing in minutes. Okay, so it is relatively simple to convert this thing in minutes. So we have to compute polonium at 0 is what? It is 10 grams. Sorry, 100 grams. Okay, and what we have to compute P at 90 seconds or 1.5 minutes, you can say. So we have to compute polonium after 1.5 minutes. Okay, so the units of time should be same here. Okay, in both things, either the rate of decay should be in seconds, or the thing which you have to compute should be in minutes or seconds. जो भी है, दोनों को same units में होना चाहिए. Rate, because the rate is given in per minute, so we converted this 90 seconds into minutes. अच्छा, rate हमें per minute में given है, ठीक है, it doesn't have any problem. So हमारे पास जो differential equation है, what would be the corresponding differential equation in this case? Two people want to join in. Let me allow them to join. Now, the mathematical model corresponding to this situation is what? dn, sorry, p वहां पे नहीं होगा, n होगा. मैंने यहाँ पे p लिख दिया because we are denoting this radioactive material by n. यहाँ पे n होगा. So the differential equation corresponding to this physical process is dn by dt is equal to 0.231 times n, ठीक है, subject to what is initial condition? P at 0 is 100 grams, and what we have to compute? P at t is equal to 1.5 minutes. 1.5, we have to compute this. ठीक है. So I hope you can solve it. यहाँ पे decay है तो negative sign आएगा क्योंकि amount of that substance is decreasing. So we have to put a negative sign here. Now after solving it, we can easily compute n of t. यहाँ पे फिर मैंने p लिख दिया. So let me change it to n. So this is n. N of t should be is equal to 100 times e raised power negative 0.231 times t. Now we have to compute n of 1.5. So what we do, we simply insert t is equal to 1.5 here and solve it. What do we get here? 707.16. 707.16 grams. So this will be the amount of that substance after 90 seconds. So it is decaying. Initial क्या है? 100 grams है. उसकी amount of that polonium 218. ठीक है. After 90 seconds, its amount will be decreased to 707.16 grams. So बहुत सारे जो particles हैं वो emit कर जाएंगे, बहुत सारे elementary particles. So इसकी amount decrease हो जाएगी. Now, in these kind of models, the half-life is very important. As we discussed, the doubling time in the population growth models, because the doubling time is very important. A certain person who try to grow a population in a certain, जैसे कि आप चिकन ही कह लें, ठीक है, चिकन की ग्रोथ जो है, ठीक है, एक शेड में होती है. अगर इनिशियली आपने 1000 चिकन उसमें रखे हैं तो आप उसकी ग्रोथ रेट आपको पता है, तो देन द ओनर वुड बी डेफिनेटली इंटरेस्टेड इन द टाइम व्हेन दैट नंबर ऑफ चिकन विल बी डबल्ड. यहाँ पे इसी तरह कोई if there is certain amount of substance who is decreasing, who is decaying, so the people are interested in the fact when this substance will be halved. So the half-life is very important. Now, if someone asks us the third question here, what will be half-life of polonium 218? ठीक है, मीन्स कितने टाइम में ये पोलोनियम जो है ये हाफ रह जाएगा, इसकी अमाउंट जो है वो हाफ हो जाएगी. So how can we calculate it? It's just exactly like the doubling time जो हमने find किया था, उसमें what we have done in that thing, हमने कहा था कि चलें doubling time में हमने यहाँ पे 2 at p0 is equal to p of 0, यहाँ पे हमने डबल कर दिया था उसको, टाइम्स e पावर k t था. ठीक है, अब हाफ लाइफ में क्या हम करेंगे, यहाँ पे हम हाफ कर देंगे. हाफ ऑफ n of 0 is equal to n of 0 times e raised power negative mu t. ठीक है, so initial amount, if the initial amount is n of 0, then its half will be 1 by 2 of n of 0. So if we want to compute in this example the half-life of polonium, so what is the initial amount of that substance? It is 100 grams. So half of that 100 grams is 50. यहाँ पे 100 आ जाएगा. E raised power इसका decay rate 0.231 times T. We have to compute T here. Okay? We have to compute T here. That is basically the half-life, means the time in which the amount of that substance will be halved. यहाँ पे अगर 100 को उधर डिवाइड करें तो what we will have 1 by 2 is equal to e raised power negative 0.231 T. I hope you get it. If you have any question, you can ask me. Now, after solving this, we can calculate the time within which the amount of this polonium 1218 will be halved. Let me compute it here. Now, 1 by 2 e raised power negative 0.231 t. Taking natural log on both sides, you can say that this is negative 0.231 t natural log of e. Natural log of e क्या होता है? It is 1, and we can compute t. आप इसको इसकी नोटेशन थोड़ी सी चेंज कर दें, t half कर दें इसको, ठीक है? So it is mean half time, or you can say half life. Half life will be natural log of 1 by 2 divided by 0.231 negative. Now, what is this? This is your decay rate. So in general, after solving this, you can compute the half-life of that material, that substance. It is approximately, after solving this, we can say that it is approximately 3 minutes. Okay. So that polonium 218, its half-life is 3 minutes. Means after 3 minutes, its amount will be half. Kindly mute your mic. पीछे अजान हो रही है किसी. Who is this guy? Kindly mute your mics. So the half-life of that polonium is 3 minutes. Okay. Now, what is this? This is your decay rate. The general formula for half-life is what? It is natural log of 1 by 2 divided by the decay rate, mu. This is the general formula of half-life to calculate the half-life of any substance. Okay, remember this. If we are discussing population decay models, then this half-life formula gives us the half population. Okay, means this time will give us, within this time, the population will be halved. If you have any question, you can ask me. Here is another example, which is basically I'm going to discuss. Let me erase this thing first. Let's discuss another example. The initial mass example The initial mass of iodine material is iodine material. It's some certain radioactive material. Uh, material initial amount means its initial amount is what? It is 200 gram. Okay. Determine the iodine mass after 30 days. So अगर इसके amount को हम n of t कह दें, then n of 0 is what? It is 200 grams, and we need to compute its amount after 30 days. After 30 days है ये, ठीक है? So it is 30 days. If the half-life of the material is 8 days, what is this? Huh. If the half-life is T half is what? 8 days. How can we compute this thing, the amount of that iodine material? If initial amount is 200 grams, half-life is 8 days, and we have to compute the amount of that material after 30 days. Now, here we are not given the growth rate. Here, the growth rate is not given. In fact, we are given half-life. We know that the half-life formula is what? It is natural log of 1/2 divided by the decay rate, mu. Okay. So T half is given. T half is given. It is what? It is 8 is equal to natural log of 1/2 divided by mu. So from this equation, we can compute mu easily, so where the mu is what? After solving this equation, we can get the mu, which is it's written in mu is natural log of 1/2 divided by 8. ठीक है, और ये जो रेट होगा, ये डेफिनेटली क्या होगा? नेगेटिव होगा. अगर आप इसको सिंप्लीफाई करें नेचुरल लॉग ऑफ 1/2 को, तो ये ऑटोमेटिकली नेगेटिव ही आएगा. क्यों? क्योंकि नेचुरल लॉग ऑफ 1/2 को हम क्या लिख सकते हैं? By using the properties of log of 1 minus log of 2. Log of 1 is always 0, so it is negative log of 2. So it is basically, in fact, log of 2 divided by 8. So this is your decay rate. Now, you know what is the differential equation corresponding to this phenomena, physical situation? It's dn by dt is equal to some mu, which is the decay rate, times n. So decay rate, you have decay rate now, you have initial amount. Now you have to solve that differential equation, and after solving that, you can compute the amount of that substance after 30 days. I hope you get it. If you have any question, you can ask me. The next thing is logistic growth. We shall discuss this logistic growth in the next lecture. Basically, what is the logistic growth? It's basically an advanced version of the population growth models, because the growth model, population growth model, which we have discussed, is not basically realistic model. It is an ideal model where the population only grows or decays. But the growth of population, basically, it also depends on certain other things. For example, food, food and environment and many other things. Agar if you have a certain amount of bacteria in certain region, if they don't have food or the temperature is not favorable to them, then there will be effect on the growth of those bacteria. So these kind of factors can be included uh, in the population growth models and also in the decay models. We shall discuss, and also the maximum possible growth of bacteria in certain situation. So these kind of uh, factors we can add in the mathematical model. We shall discuss these kind of models in the next lecture. Now, if you have any lecture uh, related to this this topic which we have discussed today, you can ask me.